Hey guys, good afternoon. My name is Bernard James, and welcome to Team Algo Alpha, where we discuss algorithms, we dissect it and break it down so that anyone can understand them. Today, my group and I will be discussing the binary search tree, and that will look like this. I will be talking about the binary search tree. Digonto will go ahead and hit us with the class nodes. Mustapha will take it over with talking about insertion, get min, get max function. Ibrahim will hit us off with the search function. Linqing will talk about the remove function, and I will take all of that and summarize it and make it into gold. All right, to start, why do we call it a binary tree? It's real simple. We can only have two subtrees from our root. And what that looks like is our left tree and our right subtree. In comparison to the root, the left is going to be the lesser value. And in comparison to the root, the right will be the greater value. And a breakdown of all of that will look exactly like this. So from our root, we have our parent node, and from our parent node, we have our leaf and our child class. So in comparison to A, our root, B would be the lesser value. And if we move down B, E in comparison would be the lesser value, where F would be the greater value. And if you see here, we see C, but we don't normally have a C on a binary search a tree or a binary tree. We normally would have a D. And so we would move over to D, which would be greater than A. And when we move down our tree, we'll have G and H, which H would be greater than D, and G would be less than D. A cool feature that the binary search tree has is that it searches with the log time of it searches with the time complexity of O log n, which pretty much means it half its search every time it goes through the tree. One of the operations that you can find in the binary search tree is insertion, the search, remove function. And all of our operations, they start at the root and make its way down. So again, with the time complexity, if we have 8 elements in a binary search tree, each time we go through, we would half. So we would move from 8 to 4, and from 4, we would go to 2, and from 2, we would go to 1. And that would make 3 iterations through the tree with the search complexity of O log n. And what that looks like is if we were to search with the number 14, we would compare 14 to 8, and we would know that 14 is a greater value, so we would move to the right, negating everything on the left. So we would not have to focus on any of the left side. So already our tree is cut in half. So we would move down the tree and do a comparison until it finds its value. Same thing if we were to look for a value on the left side. So let's say 7. We would move to the left side, which would negate everything on the right side and cutting it in half, and we would move down the tree until we find our value of 7. So all of this will be discussed primarily by each individual in my group. Thank you so much.
Hi guys, my name is Digonto, and I'll be explaining the node class portion of the binary search tree algorithm. So if we take a look at the code of the node class, we see that when we initialize this class, we take in the attributes of value and parent. So we set self.value equal to value and self.parent equal to parent. The parent attribute is added in order to make a deletion of a node easier. And we will go more in depth into this, and you'll see it become more clear when we go over the remove function of the binary search tree later in this video. Notice that we also have the attributes self.left and self.right, and they're both equal to none. That means when we initialize a node class, it will have no children by default. Also a part of the node class is an override of the string representation. From the library p format, we import the module pprint, And this allows us to represent an object as a string. So let's see this in action. If we run the node class just by itself, we can make an instance of the node class, and let's call it node x. Node x is equal to node, and then we have to have two attributes, the value and the parent. So let's just use 2 and 4, and let's run that. All right, so we can see the this function here, this overriding of the string method in action by printing this object out. As we print this object out, we see that x has a value of 2. Node, oops, let's put node x, right? Node x has a value of 2. We can also check the parent by doing node x dot parent and see that the parent of node 2 is 4. We can also check to see if it has children by using the left-right methods. Let's print that. Right. As we can see, node x has no children and it has the parent value of 4.
All right. So in order to create a binary search tree, we need to define a class. We'll name the class binary search tree. As any ordinary class, we need a construction function to be able to create objects from the class. We define this function by def underscore init and tick self and the root as a variables. And we need to be able to print out the data from the class. As a first investigation into the tree, we defined a function called empty. This function will return none if we have an empty tree. So now let's discuss the insert function. As you can see, we define 2 types of insert function. The one that public, which means available outside of the class, and the other one, which is private. We use double underscore in the front of the private function inserts. Now let's dive into the code. So as you can see that if we insert a value, we check if we create a new object from the class node. Now we investigate the tree. If self empty return for us none, it means the tree is empty. So we assign this value to the root. Else we take the parent node, we assign it to self root, and we use a while loop to check if this value is less than the parent node, we go to the left. If greater than the parent node, we go to the right. Now let's see this in more visual. Assuming we have the values 14, 12, 11, 13, 17, 15, 18, and we want to add these values into the tree. Now the tree is empty. So we send in 14, and 14 now take it as the root. We send 12, 12 is less than 14, go to the left. We send 11 is less than 12, is go to the left. We send 13 is less than 14, go to the left, but is greater than 12, is go to the right. With 17 the same, it's go to the right. Then when we add 15 is go to the left of 17, and when we add 18 is go to the right of 17. That's all what I have to say about inserts, and thank you guys.
Hi, this is Ibrahim Diallo, and I will go over the searching algorithm for the binary search tree in this particular code. So we define a search function that takes the self and the value we will be searching for. First, we start searching for the value in the root node. And if the root node is empty, an index error is raised to show that it is attempting to access an index that is outside the bounds of the list. Else is a root node. Now we use a while loop. So while the root node is not known and the value we are searching for is not in that node, the root node is now the left node if the value is less than the value in the root node, and the right node otherwise. And then we return the value in this particular node. I have an example of a binary search tree, and I will show you the example in more details. So here we have an example of binary search tree with the root node 8. Now we are going to search for the value 14, which is here. So the searching algorithm will go and compare 14 to the value in the root node 8. So step first, 14 is greater than 8, so we go right. Step 2, 14 is greater than 10, which is the new root node. We continue going right. And then we find our value 14 and we return it. In that case, it exists. Okay, searching for value 7, for example. 7 is less than the value in the root node, which is 8. So we move to the left side. Now the new root node is 3. 7 is greater than 3. So we move right side. The new root node is 6. 7 is greater than 6. We keep moving right. And then we find our value search, our value 8. So just in case we don't find our value, it will return none. Thanks for watching.
Hello everyone, the part I'm going to cover is binary search tree algorithm within the remove functions. So you have two cases when you have one children's, right or left children's, and the second case is when you have two children's, left and right children's in the same time. So the first case is when, let's say, remove the value 14, you only have one left children's in here, 13. The right children will be none, which means there's no right children's. So we were searching for the value of 14 to see if where the left or the right is none. So when the right is none, it will just assigning the 13th parent into the, make the children of the will try 13th parent into the value of 10. So the power of 14 will be just removed from the functions. And the second case is then we have two values. For example, we have the value of, we are going to remove the value of 6. So we have two children, 4 and 7. So it will go get the maximum value of left node, which is 4, and then just assign this value to the children of these lips. So the 4 will be removed, the 6 will change to 4. So that is the end of this sessions. Thank you so much.
All right, great. So in summary, we were able to see how the binary search tree algorithm works. Digonto was able to explain to us how the nodes are created. Mustapha was able to explain to us how the insertion algorithm works. Ibrahim was able to explain to us how the searching algorithm works. Linqing was able to explain to us the removal and the reassignment of nodes. So thank you all for watching this video. And if you have any questions, feel free to reach out. Have a great day.